In this example, we have a fire truck which is moving down a road, a flat road. It's moving with a constant speed. And for whatever reason, as this fire truck goes down the road, the ladder on the back is being raised at this constant rate of zero point 0.3 radians per second, and the ladder is being extended at a constant rate of b dot, which is 2 feet per second. What we want to do is find an expression for the acceleration at the end of the ladder P whenever the length of the ladder B is 25 feet and the ladder is at an angle of 30 degrees. What we're going to do is use the moving reference frame equation. So the first thing we need to do is choose who our observer is. So it's always good to start out by explicitly saying who your observer is. The observer I'm going to choose is one which is on the ladder. Okay, so it's on the back end of a ladder where that part of the ladder is only being raised. As that. I'm going to use a set of coordinate axes here of x, y, z. I'm going to say attach x, y, z to the ladder also. Okay. So with that choice, we're now set in terms of four things. One is the angular velocity of the observer. In terms of rotation, all of our observer is doing is rotating with this rate of theta dot, and that's in the positive k. The alpha vector, that is always the angular acceleration of the observer, and so that's going to be theta double dot k. The problem says that theta dot is a constant, so that's a 0. The relative velocity term, question we ask ourselves here is, what does the observer see for point P? Well, what the observer sees is simply the fact that the ladder is being extended. Is not aware of the fact that he or she themselves are rotating at the ladder is. All they see is that extension. So the extension is in the x direction. Its rate is b dot, like that. And so again, the observer is looking at end P, and all they see is that extension, so that's a b double dot I. Well, since b dot is a constant, then b double dot is a 0. So the last thing we need to do then is choose our point of reference. I'm going to choose point O. O is the attachment point of the ladder to the truck. So AP is equal to AO plus the acceleration of P seen by our observer. We have a 2 omega cross VREL term. We have an alpha vector crossed with RP with respect to O, plus omega cross RP with respect to O. It's our usual equation. Well, O is on the truck. The truck's moving on a straight line path at a constant speed, so that's a 0. The relative term, acceleration, we saw above that was a 0. The omega, that's theta dot k, cross with VREL. VREL was a b dot I. The alpha vector, that was seen to be a 0. And then we have the omega cross r, so that's theta dot k crossed with theta dot k across with a vector going from O to P. That's just the distance B in the eye. K cross I is a J, so this is a B theta dot J. So whenever I do my Coriolis term, the 2 omega cross V rel, I get a 2 B dot theta dot J. And then K cross J we know is a minus I, so that becomes a minus B theta dot squared I, like that. So that's the acceleration of the end of the letter P, like this. So let's go back to see what we did. First thing, as always, we choose our observer. I chose to put the observer on the ladder because the path that the observer sees for P is very straightforward. The path of P is not quite so simple as this in actuality, but what our observer sees is just the P moving outward. So that's in the X. That's where we get our V rel term. Also, since B dot is a constant in that observer sees a straight line path, that's a 0. But also the rotation of our observer is set now by the rotation of a ladder, because that's where to what our observer is attached. So that's just theta dot K, and the alpha is theta double dot K, which is a 0. Following that, it's a matter then of just using our omega, our alpha, our V rel, our A rel term all in our equation where I referenced it back to point O. The choice on O, it has to be some point on the same rigid body as the observer. O seemed to be a pretty good choice because we know its path and we know it's going at a constant speed. Therefore, acceleration of O is a 0.